Our speaker today is Shubham Kanodia. Shubham is a fifth-year graduate student at Penn State working on the confluence of exoplanet instrumentation, statistics, and SETI. Shubham will be presenting on From Pixels to Population, New Tools to Understand Dwarf Exoplanets. Go ahead, Shubham.
Great. Thank you, Prabal. Can you hear me well?
Yep, hear you great.
Perfect. Thanks for having me. So today I'm going to be talking about some of the work I've done during my PhD here at Penn State, which is mainly focused on dwarf exoplanets and basically starting from trying to find them to characterizing the populations. And that's what I mean by going from pixels to population and trying to understand them in a very holistic fashion. So let's get started. So why are planets around dwarfs important? So the big question. And that's because one of the reasons for that is the majority of the stars in the galaxy are dwarfs. That's what this histogram on the right shows based on Gaia data. And this has been shown in the past as well, that the bulk of the stars near the sun and in the galaxy are dwarfs. The second thing I would like to mention is that when it comes to the stellar mass across the spectral subtype of dwarfs itself, there's a huge variety in the properties of the stars. They almost span an order of magnitude in terms of the stellar mass itself, and more than an order of magnitude when it comes to, say, the luminosity of the star, which makes it interesting to see how do exoplanets vary or depend on the properties of the host star. So this is an extremely good test bed for that. The other thing I would like to mention is that there is enough empirical evidence now which suggests, both from transiting surveys and radial velocity or RV surveys, which suggests that planets around dwarfs have different occurrence rates and different distributions than, say, planets around solar type or FGK stars. And the other thing I would like to also mention is that there are different planet formation timescales around dwarfs compared to solar type stars, because the properties of the protoplanetary disks themselves are different, and hence the timescales involved in the formation of these planets can be different. The other advantage of finding planets around dwarfs is the planetary amplitude can be enhanced because the stars themselves are A, smaller, and B, less massive, which makes it easier to find planets, or the signals are enhanced. And this is also manifested when we're trying to find signatures of atoms and molecules in the atmospheres of these planets, because the transmission spectroscopy is relatively easier because the stars are smaller and also redder, which favors the upcoming space-based missions such as James Webb and the next flagships. So to further illustrate this point about the larger amplitudes and just drive it home. So on this plot, I have orbital period on the x-axis and then the planetary mass on the y-axis. And here I'm showing the transiting planets which have their masses measured. And then I'm coloring in red the ones that have their masses measured using radial velocity. And then the background is basically an illustration to show what is the semi-amplitude, assuming they were to all orbit solar type stars at one solar mass. And then the contours basically show the different semi-amplitudes marked over there. And I would like to draw attention to the 1 meter per second line, which has basically been the rough threshold for the past few years till now, when we're getting these new generation of RV instruments which are breaking that barrier. But so far, 1 meter per second has been the approximate barrier when it comes to the RV precision for finding new planets. But when it comes to dwarfs, and now you can toggle back and forth to see the difference, we see that if you're assuming a 0.3 solar mass star, the detection threshold lowers, and it's easier to find these Earth-like planets, especially further away from the star, simply because the star itself is less massive. But despite the fact that it is easier to find planets around dwarfs, there are very few planets known around dwarfs which have their masses measured. And that's what I'm showing in this plot over here. It's the same as the plot before, but now if I mark the planets which are around dwarfs, there are just about 40 odd planets out of the total. I believe there are 1,000 planets marked over here. Just about 40 of them have their masses measured, which are around dwarfs. So there's clearly a lot of work that needs to be done to find more planets. And that's what I did during the first half of my PhD, which is build these two instruments. On the left, I have shown the Habitable-zone Planet Finder, or HPF, which is a near-infrared instrument to find planets around Earth, mid M dwarfs, mid to late M dwarfs, which are typically peaking in the SED in the red. And on the right, I have NUID, which is an optical instrument, but because of its really wide wavelength coverage, as you can see, it goes from 380 to 930 nanometers, so almost to a micron. It has demonstrated really good precision on sky for stars ranging from solar type to early and even some mid M dwarfs. And these two are the instruments I was involved in building, testing, and deploying during my PhD. So I'll just give a quick overview of both of them. So the first one, as I mentioned, HPF, and the image on the left shows HPF when the cryostat is open down at the telescope in West Texas. It's the 10-meter Habitable telescope, or HET. And this is what the insides of the instrument look like. This was a very exciting instrument because it's in the near infrared and therefore it's cryo-cooled. And then we have to be very careful about how to stabilize the temperature on this instrument so that we're really beating down on the instrumental systematics and we can achieve the final astrophysical floor when it comes to finding these Earth-like planets using the radial velocity technique. The interesting thing I would like to mention about the Habitable telescope, or HET, is that it's a 10-meter telescope, which is really useful to find planets around these faint M dwarfs so we can reduce the photon noise or its impact on these measurements. But the other interesting thing is that it's a fixed altitude telescope, and it's probably just one of the two telescopes of its kind in the world where, in a way, it's similar to Arecibo, where Arecibo is, or I guess was, pointing at the zenith. It's a transit telescope. So HET, instead of pointing at the zenith, is fixed at an altitude of about 55 degrees, but it can still move in azimuth. So it can cover pretty much most of the sky, but it is at a fixed altitude, which has some interesting properties, which I will talk about soon. So as part of my work on HPF, I was involved in designing, building, and testing the fiber feed for this instrument. And that's basically the conduit which pipes the light from the focus of the telescope down to the basement where the cryostat HPF is sitting. And that has various subsystems involved in it. And as you can see, we start from the telescope and then we move down to the scrambler and then the agitator, and finally the cryostat in the basement. But the interesting thing I would like to point out over here, as I mentioned, that because of the fixed altitude design, the HET pupil, or this is the projected pupil on the primary mirror, changes a lot with time. So here I have this animation to show that. And what this is based on sky data from an M dwarf. And what we are seeing over here is that the HET pupil in green projected on the mirror, which is in gray, is moving as the object is being tracked in the sky. So as I mentioned, it has a fixed altitude of about 55 degrees. And then as the secondary moves across the sky, the pupil area, which is shown in the plot on the bottom right, is changing. And you can see it peaks at a certain altitude and then it goes down. And then also the centroid of the pupil, which is the most important parameter here, which is marked in X, is traversing across the mirror. Now, the problem is, if this is uncorrected, this is going to cause RV shifts in the order of many meters per second every exposure, which will basically drown out any kind of planetary signal that we're trying to measure. And therefore, we have designed this a ball scrambler system that we implement in HPF, we tested in HPF, and then we also implemented in the next instrument we built, which is NUID. And then I have in this paper, which we submitted earlier this year, we show that the RVs basically do not seem to care about this drastic change in the telescope pupil parameter. So when I say drastic, because at the peak of the exposure, the pupil, the cross section is such that the telescope is as good as a 10-meter telescope. But at the end of the exposure, because the pupil is moving away from the primary, it's basically something like a 5 to 6 meter telescope. That's the drastic change in the centroid and the pupil area. And what we see is that the RVs basically see no impact from this and are completely immunized from this change in the telescope parameters. And then the next instrument I mentioned I worked on was NUID, which is an optical instrument. And it was delivered to the 3.5 meter wind telescope down at Kitt Peak in 2019. And then we had to wait a year because of the pandemic shutting everything down. But we recently resumed science operations, and it just passed its readiness review from NASA. And now it's basically on sky and ready for public use. And as part of NUID, I was involved in something very similar, which is basically working on the fiber feed for the instrument, trying to figure out how to pipe light down from the telescope, down to the basement where the cryostat is, and how to basically make it as stable an illumination as possible. But apart from the fiber feed, I also worked on implementing this algorithm Barry-Corpi, which is used to estimate the barycentric corrections at the centimeter per second level. So NUID is trying to reach a much lower instrument threshold than HPF, because around solar type stars, we need the lower precision to find these smaller planets. And therefore, we need the centimeter per second precision when it comes to barycentric corrections to really reduce the instrumental flow. And now this algorithm is also used in other instruments or similar instruments, be it HPF, NUID, Express, and so on. But the important thing over here I would like to mention is you have this algorithm which works great, but to feed in that algorithm, you need some very good parameters, very accurate and precise parameters. And one of those is the midpoint of the exposure, which is what we measure using an exposure meter. And this has been done for a while now. We get fluctuated midpoints, be it from the time of the Corelli and LED spectrographs to high-res and HARPS and so on. But the interesting thing over here is that we're not just getting the fluctuated midpoint, but a chromatic fluctuated midpoint. This is especially important for NUID with its wide wavelength coverage, because the blue flux is changing in a very different way than, say, the red flux. If a cloud comes in, the dust conditions are changing. And therefore, we have this low resolution spectrograph that I helped to build and test and finally deploy, which helps us estimate these very precise midpoints at the few milliseconds level, the few hundred milliseconds level. So this was the instrumental section of my work at Penn State during my PhD. But the next part I worked on is the astrostatistics, and in particular, mass-radius relationships. So mass-radius relationships can be very useful to constrain the planetary composition. So if you have the mass of the planet and the radius, you can estimate its bulk density. And as soon as you know the bulk density, you have a rough idea of, is the planet gaseous, is it rocky? If it's rocky, does it have an atmosphere on it? What kind of an atmosphere? What's the composition, or what's the fraction of the atmosphere compared to the core? And so on. But also, when it comes to a survey like TESS, it can be very useful to predict one quantity from the other. So TESS gives us the radius of the planet, but we have no idea about the mass. So we can use these empirical mass-radius relationships to have a rough understanding of what should its mass be. And that can help drive follow-up efforts to see, okay, this is an object of 3 Earth radii, which has a mass, predicted mass of X. And that means for a n sigma mass measurement, I'm going to need approximately these many RV points. And it can basically help schedule and really inform these surveys well. So as far as my work was concerned on this, what we did is we moved away from these parametric power laws of mass radius distributions based on the work of Ning et al. 2018, who developed these non-parametric methods using Bernstein polynomials. And then we applied this novel technique to M dwarfs. And the purpose of doing so was to compare the previous mass radius work that has been done for predominantly Kepler FGK stars to how do they compare with M dwarfs. And you notice that will be the theme throughout this talk and my work, trying to see how do planets around M dwarfs differ from those around earlier type stars. So the plot on the right basically shows the M dwarf planets as they stand right now. There are about 49 or so M dwarf planets which have their masses measured. And we color them by the host stellar mass because there's such a wide range of stellar masses that they span. And the interesting thing we found, or the question we're trying to raise, as I mentioned, is, are the two distributions different when it comes to an M dwarf sample versus a Kepler sample, which is predominantly FGK dwarfs? And the plot on the right is basically showing the posteriors for the predicted masses for a bunch of different radii. So for example, the one on the top is showing what are the posteriors for the M dwarf sample, and then the one on the bottom are showing what are the posteriors for the Kepler sample. And there is tentative evidence which suggests that the mass radius distributions are different between the two on the basis of what this plot shows. But at the same time, I should also mention there are a few caveats you should keep in mind. That one, there is a sensitivity bias here. It will be easier to find smaller planets around M dwarfs than solar type stars. The other thing I should mention here is that the M dwarf sample in this case is dominated by the TRAPPIST system of planets, which definitely skews the result. The other thing I should mention is because the sample is so small, we really need a lot more planets to make an equitable comparison between Kepler or the FGK sample and the M dwarf sample. And that's what I did for the next part of my PhD, which is basically I was involved in the TESS follow-up. So we first built these two instruments, HPF and NUID, and then using the planet candidates discovered by TESS, we're trying to follow up on them and measure their masses and confirm these planets, and really improve the statistics we have on these sparsely populated M dwarf parameter space planes. And these are what those planets look like. So on the left, we have the same 50 odd planets that I mentioned earlier. And I've colored or I've circled the ones that we're currently following up on. And since we are following up on them, we do not have their masses. These are the predicted masses on the basis of the mass radius relationship. And then the ones that are in solid are the ones we've already published. And then on the right is a similar plane, but instead of mass radius, there's mass insolation. And the purpose of doing that is to see, do we see a dependence on insolation when it comes to these planets? In particular, we could talk about phenomena such as the radius valley or the Neptune desert. And some of these I will allude to in subsequent slides. One crucial point I would like to note over here is that when it comes to M dwarfs, and I have mentioned this in the past, the luminosity difference across the spectral subtype itself can be quite vast. So therefore, even if you're orbiting in the same orbital period, around an M0 versus say an M8 like TRAPPIST, the range in insolations would be quite large. And that would be even more the case if you're trying to compare the M dwarf sample with say a solar type sample. And therefore, I think it's imperative to consider not the orbital period, but when you're talking about any kind of physical process that depends on the host star, we consider the insolation flux. So one of these systems that I worked on is TOI 1728, which is a super Neptune around an early type M dwarf, an M0. The really interesting thing about this system is that we were able to obtain spectra for this planet during its transit. And using that, we can place limits on the atmospheric escape of helium-10-830, which is basically a tracer to measure the amount of atmosphere that the planet is losing. And that's commonly attributed to photoevaporation or high energy ionizing radiation from the host star. So in this case, we do not detect any measurable absorption in the helium triplet, which basically means that we can place an upper limit on the loss in helium and also the overall mass loss rate of the atmosphere for this planet. The other system I worked on is similar to the first one. It's also a warm super Neptune, but this one sits right in the Neptune desert. So the Neptune desert is this perceived underdensity of planets, which are warm and Neptune sized and Neptune massed. And again, typically it's also depicted as radius period, but again, for the same reasons as mentioned earlier, I show it as radius insolation. And this is crucial because if we consider radius period, there are a lot of M dwarf planets in that radius period regime because they can exist there without losing their atmospheres. But when we start talking about the same insolation levels as the original sample that was used to measure or depict the boundaries for this Neptune desert, we see that there are very few M dwarf planets there, and therefore addition of planets such as TOI 532 is helpful. It's helpful in trying to understand what makes these planets hold on to their atmospheres where most other planets cannot, and they either lose their atmospheres and go towards the rocky side, or they accrete a lot more gas and they become gas giants such as Jupiter's. And therefore, the efforts that we are undertaking into characterizing and finding such planets using the help of TESS should help understand this in the future. One interesting side note I would like to talk about is this serendipitous observation of a stellar flare around VB10. So VB10 is a ultra cool dwarf that we've been observing with HPF as part of our guarantee, as part of the GTO, trying to find planets around these late M dwarfs. But during one of these observations, we found a flare around the star. And the interesting thing is not just the flare, we see this red excess in the helium triplet So the helium triplet at 10^30 angstroms is in excess. It's emitting light, so the material is extremely hot during the flare. But more importantly, what we see is that there is some material that has been ejected up above the star, presumably in the chromosphere or the corona of the star, that is then raining down on the star. But at the same time, it's hot and dense enough such that it's emitting. And we measure that using our high resolution spectra. And yes, stellar flare observations have been done for a while now, but high resolution spectra such as the one we have and near infrared spectra is extremely important for such M dwarfs again, because that's where a lot of the information is, that's where a lot of the spectral features are, which have not been studied in the past. So what does this look like? So coronal rain is not a new phenomena. It has been measured around the sun. And this is a very cool animation that I would like to show from SDO, which shows the phenomena for the sun. This is not for a flare, this is for a prominence, but it still shows the downward motion of the material along those magnetic loops. And maybe we do not have enough evidence to say that what we detect around BB10 is coronal rain, but that there is some tentative evidence which suggests that what we're seeing could be coronal rain or a chromospheric condensation phenomena. The other interesting thing that this lets us do is place limits on photoevaporation. Because we've measured this flare, we know the energy of the flare, we can place some kind of limits on the frequencies of such flares. We can place limits on how much atmosphere would a planet lose if it were to orbit BB10. So this is purely hypothetical because so far there is no confirmed planet around BB10. There have been many speculations in the past, but there isn't any confirmed planet. So if there was a hypothetical planet around BB10, what would its mass loss rate be? So that forms the extent of the work I did or have done in the past and present for my PhD. And then the next slides will talk about the work I would like to do in the future, which is basically combining what I've done in the past and taking it to the next step, using these instruments we have built, using these astrostatistics tools that we have helped develop, and combining them and trying to understand these M dwarf populations better. So in sight of that, there are two main science goals that I would like to talk about today. One of them is the radius valley, and I mentioned this very briefly in the past few slides, but the radius valley is again this underdensity in the radius histogram of planets, somewhere around 1.7 to 2 Earth radii. And it's a very interesting phenomenon because we do not know what's the exact formation mechanism for the radius valley. There's a bunch of theories. It could be photoevaporation, it could be core-powered mass loss, it could be gas poor formation. Those are the three main theories, but we do not know which exact theory it is, or if it's a combination of the different theories acting in different parameter spaces. So what I'm proposing to do over here is, one, find more planets which sit near the radius valley using TESS and HPF and NUR and these really precise instruments. Two, we combine the parameters we estimate for these planets. And the parameters I'm talking about here are the planetary mass, the radius, the insolation flux, the stellar mass, and the stellar metallicity. So we are fitting this n-dimensional framework using the same non-parametric method. And the advantage of non-parametric is it's a lot more model independent. We're not assuming that the physical phenomena we're trying to model has to be in this very clean power law. And those power laws are very hard to extrapolate into multiple dimensions. If you note, most of the studies that have been done which look at the radius valley, and there has been some great work which has been done to look at this, have focused on two dimensions, be it how does the radius compare with the period or the insolation, how does the radius valley evolve as a function of stellar mass, or so on. What I'm proposing to do over here is fit a 4 or 5 dimensional framework, which we combine all these different parameters and try to find trends between them. The second science goal I would like to work towards is giant planets and how do they occur around M dwarfs. Is there a difference in the giant planet population of M dwarfs versus FGK stars? But more importantly, within the giant planet population of M dwarfs, there's some work I'm doing right now which shows that the RV sample is quite distinct from the transiting planet sample. When it comes to the planets that have been discovered by RV surveys that have just the M sin I mass measurements and not the true masses, versus the transiting planets that have their true mass measurements, there seems to be a distinct difference in those samples. So what I would like to do over here is, again, use HPF, use NUID, use TESS to find more planets, because as I will show in subsequent slides, these planets are extremely rare, at least so far as our surveys show. So A, find them, and then B, try to understand how they're different from how the two samples are different. So what are the tools? As I mentioned, I'm going to use the RV instruments that we've helped build. And the second thing that would be important to any of the science goals mentioned in the previous slide is estimate the occurrence rates for the TESS discoveries. But in this case, I'm not trying to estimate the TESS occurrence rates for all planets, period. What I'm going to suggest is doing it for the TESS M-dwarf planets and in two distinct bins, where one, we're limiting ourselves to the smaller planets, which is lesser than 4 Earth radii. And then we're doing the giant planets, or the greater than 4 Earth radii. And once we have the occurrence rates, once we have the RV mass measurements, the radii from TESS, I propose to combine these into this non-parametric framework, which is about 4 or 5 dimensions. And a very rough schematic of that looks like this. So we're combining the TESS measurements with the HPF and NUID mass measurements. We estimate the occurrence rates. And then finally, once we have all those pieces of the puzzle, we can put that in this non-parametric framework and see how things evolve. So the final piece of the puzzle is this non-parametric framework, which I've mentioned in the past when it comes to these mass radius relationships, but how does it fit in when it comes to these n-dimensional 4 or 5 dimensions? How does that work? So to give an example of that, and this is extremely preliminary work, what if we look at the radius value, not as a gap in the planetary histogram, but if you look at it in the context of the planetary density or the bulk density, and how does the bulk density evolve? So the reason we can do this is because the radius value is basically straddling two different planetary regimes. Around one side, you have these rocky, higher density super Earths. On the other side, you have these gaseous, lower density sub-Neptunes. And therefore, there's a distinct difference in the densities of these two regions. So if we can track the density and how that is evolving as a function of these two parameters, that's a distinct marker of where the radius value sits, this transition between rocky and gaseous. And that's what I'm showing with this slide. So the y-axis has the planetary bulk density. The x-axis has the insolation. And then the different colors represent different radii. So the way this is working is we're taking these 4 dimensions, the planetary mass, the planetary radius, the insolation, the stellar mass, and then we're jointly fitting all 4 of them. And then we are marginalizing the 3 dimensions that are shown over there to predict what is the mass of the planet. So in this case, for example, I'm trying to ask, what is the mass of a planet around the star of 0.7 solar masses with an insolation of, let's say, 10 Earth insolation, and a radius of, in this case, let's say 1.5 Earth radii. So what's the mass and what's the subsequent density? And that's what's plotted over here. The key thing I would like to for you to take away from this plot is that there's this transition in the bulk density for example, 1.5 Earth radii planet as it moves from rocky, which is the so anything above. So the dashed line basically shows the density for Earths. This is the rocky regime. As it transitions from rocky to gaseous, as the insolation reduces. So as we're moving away from the star, the planets are getting less dense. They're getting more atmosphere. They're accreting more gases, and we can see that transition in this framework. And that's the really important thing I would like to show over here. That as the radii reduce, as the insolation increases or reduces, depends how you see it, the bulk density is transitioning. At the same time, now where's the 4th dimension? Where's the stellar mass? And that's the crucial thing I would like to also talk about here. And I'm going to blink through these slides. So 0.7, 0.6, 0.5. As I blink through these slides, you can see that the slope of the fall in the bulk density is changing in its position, as in at what insolation are things falling, and also the magnitude of the slope. So things are falling at a different place and with a different rate, which is very important. And this is not something that has been shown in the past simply because there are very few planets which have the masses measured, period, let alone around M dwarfs. So what we can do over here is we can combine the occurrence rates measured from TESS and then use these mass, radius, and other dimensional frameworks. So it's like MR plus frameworks, combine them with these occurrence rates, and we can try to predict what the bulk density would be for the population and not just a sample, and see how that favors one theory of formation versus the other. So that's what I would like to work on as far as the radius valley science goal is concerned. The other thing I'm interested in, and I alluded to this in the few slides past, is giant planets around M dwarfs. So there are very few giant planets around M dwarfs. But what we are seeing is that the giant planet sample from radial velocity surveys seems to be different from that around transiting surveys. Now, the question over here is, are these actually two different populations? Or are we talking about is the difference seen because they're different parts of the same population, because they're at much large, very different orbital periods? The transiting planets are typically at an orbital period of like 5 days, whereas the RV giant planets around M dwarfs are at an orbital period of about 300 times greater, something like 1400 days, many years. So are they forming differently when they're at different separations from the star? Or is it that a lot of the planets that we see, or a lot of the objects that we see around discovered from these RV surveys are not really planets, but might be brown dwarfs? And in which case, there's the question of, do they form by core accretion? Do they form by gravitational instability? And if these two different formation mechanisms have different correlations when it comes to, say, the host star. So those are the kinds of questions we're trying to answer, or I would like to answer in this for these planets. And then we can do this by comparing the occurrence rates from these RV surveys that I've listed over here, and then the occurrence rates from the TESS M dwarf sample. And there's one very subtle caveat that I would like to highlight over here. When it comes to these giant planets, especially Jovian planets, as you all know, that we start to deal with electron degeneracy pressure. So it's important to have these mass measurements, because otherwise, if we have an object of, let's say, 9 Earth masses or 10 Earth 9 Earth radii or 10 Earth radii or 1 Jupiter radii, we do not know if it's a planet, if it's a brown dwarf, or it's an M8 late type M dwarf with just the radii measurements. And therefore, the mass measurements are imperative to classify it as a planet and include it in this sample. And then once we have these mass measurements and the occurrence rates, I propose we put it all into this 4D non-parametric framework. And why is that important again? So this is a plot of the two samples that I was mentioning in the previous slide. We have the RV planets in red, and then the transiting planets in blue. And just this plot itself, there are two main takeaways. One, there aren't that many giant planets known around M dwarfs. And again, here I'm classifying everything greater than a Neptune as a giant planet, just because there are so few of them right now. And two, the transiting planets are all distinctly metal rich, whereas the RV planets seem to be a lot more agnostic. The median metallicity of this sample is basically solar metallicity, and the error bars are they're basically 2 sigma away from each other, two samples as they stand right now. But the other aspect of this picture is, if I include the host stellar mass, it basically reinforces the same idea that the RV samples do not really care that the host star should be much larger or much more massive. The protoplanetary disk should have a lot more solids, whereas the transiting sample really seems to care about that. And that's the question we would like to answer. Why is there this perceived discrepancy? Is it because the median periods of the two samples are different? So as I mentioned, the RV sample has a period of about 1400 days, whereas the transiting sample is just like 3 days because of the various sensitivity and biases that are involved in each of these survey techniques. So it's crucial to understand that. And the non-parametric framework helps, because now instead of putting them as two distinct samples, you can put them into the same framework with the period axis or the insolation axis as the continuum, separating the two. And then you can also see how trends change between the transiting and RV planet samples. So if you have a dependence, a positive metallicity correlation seen for the transiting sample, how much does it change for the RV sample, and so on. And finally, I would like to mention that TESS is great for this because it's finding us these bright M dwarfs. I mean, M dwarfs aren't bright intrinsically, but relatively bright M dwarfs, say compared to Kepler. So this plot that I have on the right basically is trying to illustrate that yes, we found a lot of Kepler, found a lot of M dwarf planets around using Kepler and K2, but these were mostly validations. These were statistical validations or just radii measurements, and we did not have mass measurements. But TESS, in just after about 2 years of its mission, has already found more planets which include mass measurements than both Kepler and K2 combined. And this plot is already a month old. And I think last I checked, the number is increased by about 5 or so. There are about 5 more mass measurements when it comes to planets around M dwarfs. As discovered by TESS. And because there are so few of them right now, we can still count each one by hand. And each additional one is a big improvement and it's a big help. Yeah, so that I think is the extent of my slides. And I'm open to any questions people might have. Thank you.
Thanks, Shubham. It was a really great talk covering a whole host of different topics. I have a couple questions, but I'll let others raise their hand first. So you can use your raise hand function. If you'd like to ask a question, you can then unmute yourself and go ahead. You can also post a question in the chat and I can read that if you like. So we'll wait a minute or two before I ask you a couple of questions.
Sure.
Or seconds or two if you don't have to do questions. All right. Oh, I'll go ahead first then, because I see. Through a lot of this analysis for kind of these M's, have you broken this down kind of through the types of M's? So whether you might get to like fully convective, regions or whatever else, those types of stars.
Right, that's a great question. And in principle, we would like to do that. And as I mentioned, because you have this wide range of stellar masses, right? If you're trying to probe a phenomena which depends on stellar mass, or if the hypothesis suggests that it depends on stellar mass, just the M dwarf spectral type itself is a great way to probe for that. The problem right now is, again, sample size. When it comes to the sample size, and I don't have a plot showing a histogram of M dwarf stellar masses, but because there are so few of them, it's hard to do that in a robust manner. But I have kind of hinted at this, for example, here, where I'm showing just 3 plots. So I'm marginalizing it at a stellar mass of 0.7, 0.6, and then 0.5. And then this in principle can go down to 0.4, 0.3, where the convective boundary lies, and see how things change. So I think we would definitely like to do that. The only problem is if we do that right now, the error bars on any kind of scientific inference will be just way too large. So we need to really find these smaller planets on these cooler stars before we can do that in a robust fashion.
That totally makes sense. Thanks, Shubham. Still checking. So there's no questions. So I'll ask my other one, which is about the coronal rain and that helium measurement, which is actually, it looks like we do have a hand. I'll let Avi go first because you guys will get tired of me.
Yeah, great talk, Shubham.
Thank you.
Following up on that last question, how much, so obviously the planets, because they, originate most likely in different regions of the protoplanetary disk and migrate into wherever they are. Mm-hmm. They'll have different metallicities or sort of basic contributions of carbon, oxygen, and refractories. And so then isn't there sort of, we can't really constrain that well without obviously measuring those factors with spectroscopy, but there's a underlying unknown there that then affects this density. Are you sort of assuming in these simulations a certain metallicity ratio or iron fraction or any of these other factors?
Right. So in these simulations, for example, these 4 dimensions do not include the metallicity of the host star. But in principle, I could expand onto this and add the 5th dimension, which is the metallicity. The only reason I did not do that is because it was harder to plot a cube than a plane. And make sense out of it. But yes, very much so. The final plan would be, because if we can obtain these high resolution spectra for these M dwarfs, these high resolution spectra are great for estimating the metallicities. and moving beyond the photometric metallicity calibrations we had in the past, these spectra really allow us to get good estimates of the metallicity. And once we have good estimates on the metallicity, which do not have like gigantic error bars, we can put them in the framework. And that is the plan for the giant planets, because there we see a much stronger metallicity dependence. But when we do this analysis, I would definitely like to see if we see any dependence of the bulk density on the metallicity across these different dimensions.
I guess I was actually, that's also a factor. I was also referring more to the planetary sort of elemental ratios. So
I see.
How much iron you have compared to carbon or oxygen, some of these secondary sort of metallicity effects, which you can also get at to some extent with the stellar measurements, as Natalie Hinkle and others have pointed out. But depending on where you form in the disk, those things can be challenging to constrain. That was my only point, but
right.
Again, I don't have a great answer. I was just wondering if you are thinking about marginalizing over different scenarios for formation location.
I don't think we're doing that right now, but that is definitely a great suggestion that we should keep in mind. And if we can think about, as you mentioned, the metallicity of the planet, or if we can somehow incorporate the formation models, which if not the metallicity tell you the core fraction of the planet,
exactly,
versus the atmospheric fraction, that would be a great path forward. Yeah. Thanks. Thank you.
So I'll move on to that coronal rain question. That's a pretty cool. So you had the red excess that you mentioned, maybe evidence. For
yeah.
Yes, so
right.
So in this case, here I think you were able to constrain. I forget what you were saying. You were able to kind of constrain using kind of that excess. It was, I think, just that it might be this ejected helium that's falling back down. Based upon the magnitude of the actual residual here, can you put a constraint on how large the flare is, what the joint temperature / size of the flare is? I know for some M's you might expect really large flares, right?
Right. So we are able to place. So I'll break that into two parts. When it comes to the flare itself, we are able to place some constraints on the total energy released during the flare. And the way we are doing that is not using this spectra. In this spectra, we do not see any evidence for any continuum, a broad level increase in the continuum of the star. What we were able to do is, while we are trying to observe these spectra using HPF, we have an acquisition camera on the telescope, which is used to basically find the star and then position it on the fiber in a repeatable fashion. So what we managed to do is that use that acquisition camera to do photometry on the star, which is almost simultaneous. It's offset by like a minute or two. And what the photometry tells us is that the star itself had an increase in the continuum by about 10 to 12%. And then using that increase in continuum, we can estimate how much energy was released during the flare. So that's one part. When it comes to the helium line itself, we do a flux calibration of the helium line to estimate how much energy is released in the helium triplet in this case. And then we say what fraction of the total energy released in the helium triplet was released in this red excess. So we can say that the red excess had about, I forget, it was 20 to 30% of the energy of the total helium triplet, which is a lot considering the helium triplet, as we mentioned in this paper, was one of the brightest features we see in this flare. So all we can say is that we know about this much energy was released by this downward falling mass of matter, and it was falling with this velocity. We're trying to be extremely conservative. And the reason for that is because we did not catch the entirety of the flare. This was just, we happened to get lucky and we caught the tail end of the flare. So we do not know how long the flare has been going on for. We do not know the peak amplitude, though we try to place some constraints on that. And typically the coronal rain phenomena is distinguished from this other phenomena, the chromospheric condensation, based on the behavior during the early part of the flare. And since we have absolutely no constraints on that, and we have no idea what was going on then, we're being very conservative and not calling it out as coronal rain.
It explains a lot of the kind of tricky things that go into getting that serendipitous measurement to kind of pull.
Right.
It makes me think, you should have additional other near infrared cameras that can track things at the same time, just sitting around. But,
that would be great.
But let's see, are there any more questions? Otherwise, Shubham, are you okay? We can also pass on questions if you have them later on email.
Certainly.
But any other questions? So I don't see any more. So let's go ahead and give Shubham another hand. Thank you again for a really interesting talk, covering a bunch of topics here. And what we will do is we'll post this once this is basically uploaded. And if you have additional questions for Shubham, feel free to email him or myself, and I can pass it on.
Great, thank you.